Hey all, welcome. This is the re-recording of the how to use VPSC since Monday's in class one got all kind of corrupted, and I thought about things I could explain a little bit better. So everyone, please take a look. So all I've done here is this is the new version I'm just put up. This is the second new version. All I did was uncompress it, and this is all the stuff that's in the directory. For the most part, you don't have to worry about hardly any of this, actually. So there's a directory here called Project Problems, and this has all the input files and everything that you need, and we'll go through this in just a minute. But the first thing you're going to want to do is copy all of these into the main program, a main directory, and replace all the old files that are there. Okay. Then to run it, all you're simply going to do, for those of you on Windows, VPSC7.exe, right click on that and hit run as administrator. And oh, my cuckoo clock's going. It may, I'll wait for the song to die down for a second. As you can see, it's currently running about 3 minutes and 15 seconds fast. It may ask you for your administrator password to run it, but that shouldn't be a problem. A couple people have asked to compile it on their own. The main program is VPSC 7.4. This is Fortran 77. Here's the code, and you can see it includes VPSC 7dim, and later on it will include VPSC 7 sub. But all the source files are here for you. Right? And if you want to compile it on your own, here are the flags. It's best to do it. That was how to do it for Windows. It's best to do it. Oops. That didn't open in VI. Okay. It's best to do it in G-Fortran. Here's all the flags you use. It's also, for some reason, works better if you compile it first and then build from the object file. In case you want to do any debugging, you can run that here. This won't apply to most of you who are just going to run it on Windows. If you want to compile it yourself on Windows, you can do it through MinGW or Cygwin, but it's kind of a pain right in the rear. Just use the build. That's how how I did it the first time and screwed it up, and how I had my students do it the second time and made it work. I don't know. That probably doesn't give you a whole lot of confidence in my programming abilities. But let's take a look at some of the files that you're going to use. So the main input file is this VPSC7.in. And this has, there's nothing in here that you're actually going to change. This controls all of, this is all the control, everything that controls the program is listed here. It says that our single crystal file, this we'll look at in a minute. This is all of the properties of the material is in this file. Our texture file is listed here, and this file gives our deformation path. Like I said, you don't have to change anything, but everything is, this is what controls what's going on. Now, the texture, this ran text, because it's got a TEX open in LaTeX. This is just a list of 500 grains, and this is the 3 Euler angles for the grains, the 3 Euler angles for each grain, and this is the weight. So here they're all these orientations are equally weighted, and they have crystal orientations that are randomly sampled. The other file, again, you won't need to modify this, but it's important just to kind of see it. This is the deformation. All right? So this is the where we apply the boundary conditions for the simulation. So here we're applying mixed boundary conditions. So where the 1s are means that we're enforcing the velocity gradient. Where the 0s are, it means we're not. Down here, the 1s mean we're enforcing the stress for those components, and where the 0s are, we're not. So we're enforcing that there's no shear, macroscopic shear, and we're giving it a compression at a quasi-static strain rate of 1 times 10 to the minus 3. We're letting these two terms float, but we're providing an initial guess. And then we're saying down here, because we're enforcing these two stress, that there is no longitudinal stress boundary conditions being applied. So that means over all the 500 grains, these components of stress should average to 0. And this is meant to mimic a standard compression test, where you'll have a stress, macroscopic stress in the z direction as you're compressing, but your sample is free to expand in the x and the y direction. Okay, so the one that you will eventually be making some changes to is the single crystal file, or SX. So up here, it has the information about the unit cell. It's austenite. It's a cubic material. All right, has a cubic crystal symmetry. These are the unit cell ratios. A, B, and C are all 1. The unit cell angles are 90, 90, 90. This is the elastic stiffness tensor in GPa. Thermal expansion coefficients, which we don't need. Now what this says is we have 2 deformation modes. 111-110 slip and 111-112 twins. Those are the possible deformation mechanisms in this material, but we're only going to consider, this is the number of modes used in the calculation, we're only going to consider 1, and we're only going to use mode number 1. So for this, we're only considering slip. Okay. This lists all the possible slip systems that we should consider in the calculation, and we say how many of them are allowed. This is mode 1. There's 12 possible slip systems. And this needs to be, I need to fix this. The number of allowed operative slip systems. Here is only 1, which will give us some weird results. So I will fix that before we give it to you. this should be right. So we want all 12 to be potentially operative at any given time. Now down here, this is saying we're using Voce hardening. It's rate sensitive. Grain size doesn't matter for this. And these are the parameters that you guys are going to play with for the second part. Tau naught, let's go take a look and I'll post this manual. Tau naught is the yield strength of a single crystal in the crystal reference frame. Right, so this is the tau, the critically resolved shear stress for the slip system. Right. Tau 1 plus tau 2, well, let's go here. Theta 0 is the initial slope of the plastic part of the stress strain curve. So we assume that we're elastic here. We go to the plastic transition. Theta 0 is the initial slope. Theta 1 is the asymptotic slope of this. And tau 1 plus tau 0 is the asymptotic value projected back to the axes here. Right, but this is for a given slip system, right? So when here in our case we have a 12 possible slip systems that are active, and it's a polycrystalline FCC. So the stress strain curve won't look like this, right? This is just the behavior of one slip system, the hardening behavior of one slip system in one grain, right? So this is from the VPSC manual. I will post that into the up on Carmen. So if you want to have take a look at it, and then this latent hardening, self-hardening, and latent hardening. This basically just says how much slip on this slip system contributes to the hardening behavior of itself, and how much it contributes to the hardening behavior of the other modes. Hold on, didn't I just change something there? Yes, I did. I wanted to make sure I wrote it before I click. Okay, so now we'll actually come here and run it. Remember, if you're on Windows, you'll just right-click on VPSC. Okay, see the simulation runs very quickly. The outputs of this, right? So we have texture, phase 1 out. This gives the final texture of each of the grains, the final orientation of each of the grains. Right? So if we also open, where's our initial texture? It's called rand. Let's open it from here. All right. You can see these are different because our grains have rotated. Right. So we have different Euler angles for each grain, and the amount that each grain rotated will be different based on what the initial orientation was. Okay. So that's the texture out. Stress strain out, right, is columns. Let me import this into MATLAB so we can. So let's import the data. Stress strain out. Okay, so we've imported the data. So each column of that I guess, yeah. I already had stuff in, so let me just do that again real fast so I know, make sure I'm looking at the right things. So each one of these columns is different. This is SVM is the von Mises stress. These are the different components of the Cauchy stress. Von Mises strain, different components of the strain tensor. So let's just plot the von Mises strain, von Mises stress and strain. All right. So here's our stress and strain curve, and our stress axes. I said in the hardening file, I said the original the yield strength of all the slip systems was 1. So the units of this stress can be interpreted as a scaling of the critically resolved shear stress for the initial critically resolved shear stress for slip in our material. So the macroscopic yield strength of the material is almost twice the critically resolved shear stress, right? Which makes sense. This is a polycrystal, right? Not all the grains are oriented for easy slip, right? And so at the initial, you need to apply significantly more stress to get your sample to deform than the critically resolved shear stress, right? And we took this out to a strain of 1 in 50 increments, right? And that's what our stress strain curve looks like. So a couple other files that you need: stats.out you can ignore, runlog.out. This basically writes everything that happened in the calculation. So if you're getting odd results or something isn't working right, send me this runlog file, and that will help me troubleshoot what the problems are. Initial strain rate out. This gives at step 1 what the strain rate is in each grain. These are the 5 components of the okay, this I need to fix. I'm glad I've gone through this. So these are the components of the strain rate written out, but they're not in a useful form. So we'll post a new version of this up tomorrow. But this will have the 6 components of the strain rate in the normal Voigt notation that you're used to. This is the strain rate at the final step, and there'll also be 2 files for the grain stress initial and grain stress final. So that's it. So if you have any other problems, just let me know, and I'll get another new version up tomorrow that fixes these write-out issues. Okay, thanks guys, bye.